Here in number 11, they want us to figure out the potential of this galvanic or voltaic cell. And so we know we have gold ions and copper ions making it up. And their concentrations are not 1 molar. So this is not a standard cell. And so we'll have to go ahead and use this full equation here, where we adjust for not being at standard conditions. But before we do that, let's go ahead and figure out what's being oxidized and what's being reduced. So here I've written both of the reduction reactions for the gold and for the copper, and I can pull their values for the reduction from the table and pick which one is going to be reduced based on which is better at it. So both of their potentials are positive, but the gold potential is definitely more positive. So it's more spontaneously reduced than the copper. So we'll say that's the reduction reaction, and then we'll flip the copper reaction, and it will serve as our oxidation. And when I did that, I also flipped the sign to make it now the oxidation potential of copper solid. And now we can add those two potentials together to get our standard cell potential. And the value we get is a positive 1.353 volts. Okay, but that's not what we're going to circle because we're not at standard conditions. We're going to have to use that value here to figure out our non-standard condition potential. So we'll need to figure out what Q is, but to do that we'll need our overall reaction. And we can see right now that we're not balanced in terms of electrons. So we'll have to balance our electrons by multiplying this top reaction by 2. And so now when we combine our two half equations, the electrons will cancel, and we'll have an overall reaction that's 2 gold ions reacting with solid copper to produce 2 solid golds and a copper ion. And so when we want to figure out Q, we'll do aqueous products over aqueous reactants. So we'll have our concentration of copper ions divided by our concentration of gold ions squared. And those values we'll get from underneath the beakers above. So we'll have 0.2 molar divided by 0.05 molar squared as our Q value, which ends up being 80. And so now we can combine our standard E with our Q to figure out our non-standard cell potential. So we'll have our 1.353 volt standard potential minus 0.0592 divided by N, which is the number of electrons transferred in the reaction, which is 2 here, times the log of Q, which is 80. So we can plug this in and we'll get a potential that is 1.297 volts. So this is a lot like the problems that we did for exam 2, just slightly different because we're working in volts instead of kilojoules. In number 12, we're trying to figure out how much nickel we can plate out if we were running a current in 1.2 amps over the course of 2 hours. So here I've written the reaction that would take place at the cathode, where we're adding 2 electrons to the nickel to make that solid that we're interested in. And so when you see amps, I always automatically write it as 1.2 coulombs per second. Okay, so I'm going to start with what I'm given. That's not a ratio, that's just a number. That's going to be my 2 hours. And I can connect from time with my current, that 1.2 coulombs per second. But first I need to get the units to match. So I'll say there's 3,600 seconds in 1 hour. And then I can say that for every 1 second, I'm putting in 1.2 coulombs. And then here, it might seem like I'm stuck, because I don't have anything else with coulombs in it. But what I do have is Faraday's constant, which is on the data sheet, which says that there's 96485 coulombs of charge per 1 mole of electrons. So I can use that number to convert to moles of electrons. Okay, then I look up in my reaction and I don't have 1 mole of electrons. I'm going to have 2 moles of electrons. And for every 2 moles of electrons that I put in, I'm going to get out 1 mole of nickel. They're not asking me about moles of nickel, they're asking me about grams of nickel. So I'm going to have to use the periodic table to get the molar mass of nickel. And then once I've landed in grams, which is the unit I'm interested in, I can multiply through to figure out just how many grams of nickel that would end up being. And it ends up being about 2.627, so it's 2.63 grams of nickel, which corresponds to answer choice E. So don't be afraid to write your units. Units are great. They really help you see what you need to do next. And don't forget Faraday's constant, and to write your reaction so you can see how many moles of electrons you actually have to put in. In number 13, they're asking us which of the following will decrease the cell potential for the following voltaic cell. And this is written in the simplified notation, which goes alphabetically. So this first portion will be what's going on at the anode, and this portion will be what's going on at the cathode. So I know that the zinc is being oxidized and the silver's being reduced. And I'm realizing now I accidentally wrote in gold. Okay. So they're asking us what will decrease the cell potential. And so if we're decreasing the cell potential, we're becoming less spontaneous. So we want to look for what would give us a shift to the left. So this is going to be a Le Chatelier question. So in A, it says increasing the size of the solid zinc electrode. And that's not going to be the case. That's not going to cause any shift, right? Because it's a solid. We don't think about them as being involved in equilibrium. So B is also out. Okay, and then C says adding water to the anode. So that would be like changing the concentration of our zinc. It would be diluting the zinc, so it would be like decreasing that amount. And we know if we decrease the amount of our product, we'll end up shifting that direction. And that would cause an increase in the potential, not a decrease. So that's not going to be the answer. And then in D it says adding KBr to the solution to form solid a GBr. So what that would do is remove the silver from the solution. And when we remove a reactant, we're going to shift to the left to make up for that loss, which would be a decrease in the potential. So here D would be the answer. And if we look at E, that would be kind of the opposite of what we just did. We would be increasing the silver concentration, so we would shift to the right. Okay, number 14 is asking us which of the following sparingly soluble salts would be more soluble under acidic conditions. So what we want to look for is if in any of these solids, if one of the components that makes it up would be a weak base. Because if there's a weak base, or a strong base, if there's some kind of base making up our solution, then they can react with the acid that's added in and be removed from the solubility equilibrium, making the salt more soluble. So basic ions will be more soluble. Okay, so if we look at the silver chloride and use our old-fashioned acid-base knowledge, we'd say that neither of these ions are basic. Chloride's a spectator. Silver might be a pretty bad Lewis acid, if anything, but definitely not a base. Iron perchlorate, neither of those are basic. Iron is a good Lewis acid, and perchlorate is a spectator. With strontium hydroxide, strontium is a spectator. But hydroxide, of course, basic. So this would be more soluble in acidic conditions. KF, potassium is a spectator. Fluoride is a weak base. So this would be more soluble. Zinc iodide, zinc's the Lewis acid. Iodide spectator, so this will not be more soluble in acidic conditions. Okay, so our answer here is D. Number 15, we're picking which relationships about electrochemistry is false. So A says when delta G is negative, the E cell is positive, and that's going to be true, and this would correspond to when a reaction is spontaneous. And B, it says when the standard cell potential is positive, products are favored at equilibrium, and that's going to be true. We can think of this kind of as saying if negative delta G standard. If we have a negative delta G standard, we say that products are favored at equilibrium because we're spontaneously going more toward products. Okay, for C, at equilibrium, E cell equals 0, and that's true. So this is our non-standard cell potential. And if we're at equilibrium, we don't have to move anywhere, so our potential is just 0. And here it says if we have a negative E, we have a small k, and that's also going to be true. Because this would be saying sort of as if we have a positive delta G standard. We would say KEQ is less than 1 because it'd be reactants favored. And so that leaves us E, which says when Q is less than KEQ, E cell is less than 0. And so we know when Q is less than KEQ, we have too many reactants. So the reaction is going to go in the forward direction, which is spontaneous. And so that should correspond to a positive E. So this is false. Okay, for number 16, they want us to rank the salts by increasing molar solubility. And they give us the KSPs. And so what we're going to do is rank them by the X from the ice table. So we're going to have to do an ice table for each one of these. So let's start with the mercury carbonate. We're not going to include the solid. We're not starting with any of them, so we'll have plus 2x for the mercury, 2x, and plus x for the carbonate. And so our KSP will be equal to 2x from the mercury squared times x, which is equal to 4x cubed. So we can use the KSP from up above to solve for x. We get that x is equal to 2.08 times 10 to the negative 6 molar. And so make sure you can solve these with your exam calculator. Okay, make sure you can do cubed roots, fourth roots, whatever roots. Okay, so now we'll have to do kind of the same process for the silver bromide. Not going to include the solid. 0 of both to begin, plus x, x, x. So our KSP is going to be equal to the x from the silver times the x from the bromide, which will just be equal to x squared. And we can solve for x using the KSP above. And we get that x is 7.35 times 10 to the negative 7th molar. And then we'll do the last one, which is the calcium carbonate. 0 to begin, plus x, x, x. So we'll say KSP going to be equal to x from the calcium times x from the carbonate, which simplifies to x squared. And we can use our calculators to solve and get a molar solubility of 5.1 times 10 to the minus 5 molar. Okay, so to choose our answer, we're just going to rank these by the x values that we just solved. And so the biggest one is the third one. The next biggest is the first. And then the second one is the smallest. And so the right answer here will be C. So here for number 17, we're going to do something really similarly to what we did in the last one. They want us to figure out the pH of a solution of magnesium hydroxide given a KSP. So really what we're trying to do is figure out what the equilibrium concentration of the hydroxide is. Then once we know that, we can just go ahead and solve POH and then pH. So we'll use an ice table. Oh, I wrote aqueous, but this is of course a solid, right, because we're looking at solubility. And so we're not going to include it in our ice table. We'll say, didn't tell us about either of these things to begin, so 0, plus x, x, plus 2x, 2x. And so our KSP is going to be equal to the x from the magnesium times 2x squared from the hydroxide, which simplifies to 4x cubed. And we use the KSP up above to solve for x. which is 1.12 times 10 to the minus 4th molar. Okay, but we don't want just that number. We want to convert this to our hydroxide concentration. So we're going to have to multiply it by 2. We'll say our equilibrium hydroxide concentration is 2.24 times 10 to the negative 4th molar. And so from that now we can get our pH. So we can say the negative log of 2.24 times 10 to the minus 4th is equal to pOH, which is equal to 3.95. So our pH is going to be equal to 14 minus 3.95, which is going to be 10.05, which corresponds to answer choice B. And we could have ruled out most of these answers because we know the magnesium hydroxide is going to be basic, so our pH should be greater than 7, and it is.